Hello, everybody. It's my pleasure today to introduce this person who doesn't need any introduction, our longtime colleague, Professor Semyon Meerkov. Semyon's had a long history. He got a master's degree from Ukraine in 1962 and a Ph.D. From Moscow in 1966. And after working in Ukraine for a little bit, he went back to Moscow for a little bit until he moved to the US in 1979, where he joined the faculty at Illinois Institute of Technology in Chicago. Then in 1984, he joined the faculty at University of Michigan the same year as myself, and Technion, and shortly before, Stefan Loftus and Jesse Grizzle and the rest of these characters from back in the 80s. So he worked on a variety of different research topics and had many accomplishments, but judging from the title of his talk, I think he's going to tell you about that himself. And so I will let you begin. So
Thank you. Thank you.
Okay.
Such a reception, guys. And thank you for coming here in the room and on the Zoom as well. Some people came from different cities, different states, and so on. Appreciation, of course, to all of you. Thank you. So when I was asked to give this talk, I had three issues to consider. One was, should I talk about a specific topic, or should I discuss what I have been doing during the last 60 years? And I thought it would be more probably profitable for all of you rather than thinking about it. Okay, so rather than giving you a technical presentation, which would be of interest just maybe of two people in this room. So I thought I'll give just a general thing, so you will see what it's all about. So that was one. And I decided, of course, as you know, go the second way. The second, how many topics should I cover? And here I followed an advice of one of my teachers, Professor Tsipkin. And he used to say that there is no theory that you cannot explain to a reasonable person in 5 minutes. And I have 40 minutes because I would like to have 10 minutes for advice to the students, and as I promised. So I thought I will have 10 topics and I will do 4 minutes for each topic. This is number 2. So it will be 10 topics. 5 of them comes from the left side and 5 from the right side, for obvious reason. Now, the third one was what to cover and how. Obviously, in 4, 3, 5 minutes, I cannot go through technical details. So what I will do, I will talk about background of each problem. That would lead me to problem formulation. And after that, I'll talk about the approach that we used for solving this problem. And finally, briefly about the results and maybe some impact, if any. So this is what I'm going to do. So these are the problems that I will talk about. I'll not list them here. Also, I will give advice to the inspired. I hope there are some inspired. I see some of them, maybe not too many, but some inspired are here. Okay, and after that, I'll conclude with some acknowledgement. And as I said, I plan to spend about 40 minutes here, and after that, go to the rest. So the first topic is extremum seeking control. In about 60s, early 60s, researchers have concentrated quite a bit on plans of this sort. It has a dynamical part described by a transfer function G of S, and had a static part, which is defined by the extremum function, either convex or concave. Example of such plans, and this is what generated this interest, were because of the importance in power systems at the time and aircraft engine control. Now there are other areas that use similar things, but at the time that was the main application. To illustrate why it is important, if we'll talk about power system, we'll talk about efficiency of let's say, boiler, efficiency will depend upon airflow rate. Not enough air, the fuel will not burn. Too much air, it will be blown away. So there is a point which is a maximum. This is where you would like to operate. There are some other applications of this sort. In all of these plants, control goal was to optimize this function, either maximum or minimum. In other words, we should operate at the point where the gradient of function Q with respect to this variable y is equal to 0, meaning maximum or minimum. Now, unfortunately, this gradient is not measurable in real time. And therefore, various search procedures people use in order to find this extremum. Some of them have been created by Krasovsky and Fitzner. Some other people look in this area as well. Okay?
Screen.
Green went to.
There you go. Okay, so let me say okay. This is what I thought we will avoid. I have to go to Zoom. I have to go to Zoom and start it again. Okay, Zoom. And after that, share it again, and screen again, and broadcast again. It will start now.
Start sharing.
Mhm. Yeah, it's here. Thank you, Pues. So now you know where this computer business comes from. So now it is, should we charge this 2 minutes to some computer people in this department or to me? I don't know. So this variable gradient of a function is not measurable, and you have to do it by search. And as I mentioned, there are several things that have been created. The problem is that sometimes the systems work and sometimes they did not work. So the question therefore is when it does work and does not. And this is the research problem. Find out when extremum seeking systems work and when they don't work. So that's what I was studying. In terms of the system created by Krasovsky, this is the system. Krasovsky was a 2-star general, chair of the Department of Control in Russian Air Force Academy. Wonderful man, by the way. Later, he was a member of my dissertation committee, and he came to the defense with all the decorations, and so I passed it without any problem. So the system that he created had this plan that we discussed, and after there was a search signal A sine omega t added, and after he has multiplied through by this A alpha sine omega t, this called synchronous detector, and after that the signal was integrated with time constant t, and the loop was closed. Now, the equation of motions are like that. From this equation, it's difficult to see what is it that the system is doing. So some kind of analysis of simplification is necessary. And I used, as a method of simplification, the averaging theory, developed by Bogolyubov and Volosov. Volosov, by the way, was one of the major reviewers of my dissertation later on. So this averaging theory worked like that. There are states, X, which are slow because of this small parameter epsilon, and states Y, which are not slow. Epsilon, as I said, is a small parameter. So the averaging procedure that has been proposed and proved by Bogolyubov and after that extended by Volosov is the following. First, you solve this first equation for constant X, and you obtain Y of T and X. And after that, you substitute in the slow equation, and after that, you average this equation with respect to time, assuming that X is constant. As a result, you obtain this average equation. This is X now decoupled from Y, and we can see what system is doing. And this is why we will be like that. How these two trajectories are related, this is how they're related. This is the original, this is the average. There will be square of epsilon close to each other on this finite time interval, large by finite, 1 over epsilon. Now, for stability, it will not work. We need to know for stability infinite time interval. That's what property is. So I extended their theorem for this infinite time interval by assuming that average system is globally asymptotically stable. And it allows us to prove the whole thing on the infinite time interval. And that's what we applied. That's what we have done. Using this method, we did a couple of studies for indeed seeing what's happening. Now, I would like to mention that these equations are written when the plant is like that, simplest plant, first order system with a time constant tau. And this is important because as it turns out, how the system behaves depends upon interplay between tau and t. This is the simplest case of first order system. The same thing happened with any other system. You could look at dominant pole and dominant pole in plant and the t in the integrator. This is what plays around. The results are like that. When no dynamical part altogether, only static. And this dimensionless constant omega t is greater than 1, meaning epsilon is like that. In this case, this is how system behaves. With the students here, I will ask what the system do. What did the system do? I usually ask it in class. And now we see what it does. It's just a first order gradient search along function q. And the reform converges either to minimum or to maximum, depending on plus gradient or minus gradient. Now, when there is dynamics, but dynamics is small, time constant is small compared to the integrator. In this case, again, we take the same gradient search, but now with a different step, which is also okay, system is working. However, if the time constant tau and t are the same, in this case, we have a second order surge, which is okay. But the problem is that the minimization or maximization now is not q, but as you see here, q and q squared. This messes up what we're optimizing and will not converge to the right point. And finally, when tau is much larger than t, again, we have a second order surge along the square of q rather than q itself. So this is what messes up. So design it right, we have to make sure that integrate are much slower than the system itself. In this case, everything is working. This is how this issue has been clarified. Now we extend it to other systems as well. And when q is changing too, because q is not known, this function, it depends upon ambient condition, what the conditions of the plant, and so many things are coming in the picture. And we extended it, for example, when it depends upon time. The results were published in a bunch of papers in this automation and remote control journal. It's the main Russian journal in control, cover-to-cover translation in English. And in journal differential equations, which also has a cover-to-cover translation. Now, so the field, at the time the issue was solved and not many people look in this area. Suddenly in the 90s, the thing became very hot. Miroslav Kristich from UCSD, he started working in this area. Many people started working in this area. A bunch of books appeared, he and his students. Papers are still coming. The last one I saw last month. People are still working in this area. In the kind of extending various things, certainly they move forward, not the same thing. The main thing now, it's a database design of control system, not model-based, but database. And this extreme sequence system became important. You can look at the YouTube, there are stories like that and so on. So this is the first topic. The second topic was simplified description of slow Markov walks. In the 70s, early 70s, people started working on machine learning. You think that it was invented yesterday. Now everyone is doing machine learning. No, it was about 50 years ago when people worked in this area. This is how the whole thing started, and many things have been done. Now, and main equation to study in this area was like that. So this is the state of our system. Time was n+1, this is n, and this is the innovation term, again, the small parameter epsilon, to be able to study that, we put it here. And this innovation term becomes the state in a sequence of independent random variables psi. So this makes the system a little bit complex. So the problem is, how can we analyze this slow Markov walk, slow because of this epsilon? So it was clear to me that Bogolyubov and Volosov average over time. We have a random system, so we should average it over probabilities. And that's why I introduced this finite difference equation, which is deterministic, but this lowercase phi is just conditional expectation of the original innovation phi with respect to x. So that is how this thing works. So now we have a deterministic equation. We can analyze it. There is no much problem. How the two are related? Well, the theorem here is like that this is deterministic trajectory. This is deterministic, this is random. And they in probability, they're close to each other. So this sigma is small, and this sigma is small, the probability is large. And this is true on this time interval. And again, assuming that this averaged system in differential form is global asymptotically stable. The global asymptotically stable, meaning converges in a nice manner to an equilibrium point. In this case, if it's like that, the random and deterministic trajectories, they again close to each other in probability. So they kind of solve the problem, how you analyze stability processes in, let's say, pattern recognition. This is an example that if you have a system like that, which is a gradient search along the function that is a gradient of a random function. In this case, using this method, you obtain the equation like that, where this is just expected value. So we see that this gradient search random, which is the same as deterministic gradient search along the function like that. Okay, these are some papers that have been published in this area. That was continuation, quite a few people after that. Later, these papers were published 72, this one some years later, published in other areas as well. Next topic, now we talked about all of this was local search. Now we'll talk about global search. Global search, because the functions could be like that, could be a bunch of maximum, bunch of minima. In this case, what we're interested in this global minimum. How can you do that? At the time, there were some algorithms for search of global extrema, but it was not exactly clear what is the reason. So the system that they converge to global extreme. So the problem that I considered here, what is the fundamental property that leads to the global extremum, minimum and maximum? To illustrate this property, let us consider a differential equation like that. X dot is equal f to the power n of x. Well, f, you look at it as the graph that I just showed. So now we move with the speed at each point, f to the power n of x. Take initial condition 0, and final condition go to 1. So x between 0 and 1. And n, this here will be the positive integer. So in other words, start right here, move like here, with the speed proportional to the value of this function. In this case, the theorem is like that. So average value of the trajectory in the limit when n goes to infinity is exactly this global minimum or maximum, whatever it is. Here it's a minimum because formulated for the minimum. So this is a search of a global extreme. It turns out that every algorithm that existed at the time of global search was based upon the same property, and we call this property trajectory deceleration. If our system behaves somehow, but its speed becomes small, in the point where function is small, you will stay there long enough when n is large enough. This is how you optimize in global manner. Let's see, I don't have eliminate here. There is a famous algorithm that Kolmogorov-Khasminsky process. Maybe you know the name Kolmogorov. Anyone here? So Kolmogorov and Khasminsky, they developed thing, and it turns out it's exactly based upon this deceleration in the global minimum. In this paper that I published, I have also a bunch new algorithms suggested. Now, later on, quite a few years later, there appeared a new process called simulated annealing. Extremely positive, active area of research until today for search of global extreme. And of course, all simulated annealing algorithm, at least the one you looked at, they're based upon deceleration property. Okay. Vibrational control. This is the next topic. This is the area that I worked for a number of years. So if you have a pendulum, this equilibrium point is unstable. And this one is stable, asymptotically, even if there's friction. Now, people discovered the phenomenon that if you vibrate the suspension point fast enough in the field of gravity, in the vertical direction, in this case, it turns out the upper equilibrium point becomes asymptotically stable. So now you take it, deviate upper, and have to go like that. And it's not like broom balancing, what is use feedback. This is just a time dependent, nothing else. You vibrate just suspension point. Now, some people did it. There is indication some people was Maxwell. And after that, many other people about him, after him, rediscovered the same James Maxwell. Now, in 1951, Kapitsa, Nobel Prize winners in physics, rediscovered it again. Long story how he did it. If someone interested, I can tell you the story, but I don't want to use my time on that, so I'll skip at that now. The one who rigorously proved what happening was Bogolyubov when he developed this averaging theory. Now, the question was, we have a second order system. We stabilize it by parametric vibrations. Is it only for second order system that it works? Or there is another class of systems? And if this class of system is rich enough, how you select this parametric vibration that you accomplish what you want? And this is research problem, provide answer to this question and related questions as well. So we consider this problem, vibrational control, in two formats. Open loop vibrational control, that I vibrate just the plant itself, and closed loop vibrational control, when I control not the plant, but controller that now became vibrational or periodic or high frequency periodic. So this is result concerning the open loop vibrational control. First, we call the system like that, is vibrational stabilizable. If there exists a periodic average zero matrix B of T, this B of T right here, such that if I start vibrating elements of A with this B of T, the system will become asymptotically stable. And the answer is that as long as the trace of matrix A is negative, meaning the sum of the eigenvalues are in the left semiplane and some of them in the right semiplane, there is vibration that pulls over all eigenvalues to the left semiplane and make this average system asymptotically stable. Okay, and the proof is constructive and allows you also to figure out what B of T is. Now, there are extensions to other systems, not only differential equations, linear, could be nonlinear, distributed parameter system, system with random parametric vibration. Joseph did it for a system with time delay. That's correct.
My student did it actually.
Oh, your student did it.
He
Okay.
went as far as to my student.
Okay, so there are some extensions. There are a bunch of applications. Some of them we did, many other people did. For example, vibrational control of gas laser, we're involved in that. And at the time, it was a highest power CO2 laser that people created. Also, we did some work with chemical professional in chemical reactor. Plasma pinch by a physicist had retention of plasma and so on. There are a bunch of applications, including in the medical areas like that. I'm not involved in that, but I saw them happening. Okay, closed loop vibrational control. So we have now a system with like control U, and control now will be control will be calculated using the state equations for the controller itself, Z, and there's a control will be linear combination of those Z's, and the controller is vibrational. In this case, it turns out the following, that if this ABC that defines my original system is controllable and observable, in this case, there exists a periodic controller, high frequency periodic controller, that moves, relocates not only open loop poles, like all controllers linear do, but zeros as well. So if you have a non-minimum phase system, and you have these pesky zeros in the right half plane, you can use a periodic controller. So in the average system, poles and zeros will be in the left semiplane, and therefore you can extend linear control theory dramatically. You can sure increase robustness, absolute stability sector, increase decentralized control also this fixed mode in decentralized form, they disappear. So this will be that will result for this thing. Now, this is a colleague here who worked with me. One of them, one of my teachers and good friends too. You probably recognize the name, or maybe even likeliness. If you see him, probably you were born after already he passed away. Richard Bellman, the father of dynamic programming, and many other sweet good things. And my dear friend, also unfortunately late Pierre Kabamba. This is Joseph. He's right here. This is Theodore Ronaldson, unfortunately genius, but a genius person. Passed away very, very young, Ed Kippur and Sudan Lee. There are a bunch of papers that we published jointly with all these individuals I mentioned. Now, the time is going very, very fast. I will not be able, obviously, to go through the whole thing, but at least I would like to do this thing and maybe about manufacturing a few words as well. So, mathematical theory of rational behavior. I purposely selected this topic that will be more interesting for general audience, not only for control professionals. So in the beehive, bees could perform various social functions, foragers, sanitars, cleaners, and so on, builders of the comb, and so on. People calculated what is the fraction of bees in each of the social functions. Let's call it news. And the sum of this fraction will be equal, obviously, to 1. Now, people removed experimentally some of the functions. For example, with foragers, they start flying away during a good day. You move the beehive, and foragers will not find it back. So the family will die of hunger? No. They will redistribute themselves among the social function. So the same new they had before will be maintained. How can it be? They're not smart enough to do that, and who will tell them be switch and so on and so on. So the question that I wanted to address is develop a mathematical theory that will try to explain, at least hypothetically, how things like that could happen. So the theory is based upon 2 parts. First, I define axiomatically rational behavior. And after that, I form a society of these rational agents. And after that, I study what happens in this society when the actors are reasonable, rational. Will the society always be reasonable or not? So this is how the whole thing. It's kind of a little bit less statistical physics that you have many molecules that interact in the phase transition. Will it be here phase transition or not? So the behavior is defined as trajectory in the decision space, and the behavior is rational if property of ergodicity takes place, meaning that agents, they try all possible action, at least consider them. And retardation is that the rational element will stay longer in the position where this parameter of the behavior, this functional parameter phi of x, is small rather than large. So they call it retardation. You can stay longer in the good places than in bad. And the n here, this is another parameter right here. This is the memory or intelligence of this agent. So now we have this rational behavior, the behavior of individuals. Now, other individual rational behaviors in mathematics, yeah, they're all global search algorithms, they're like that. Rational agents in real life, von Frisch, one of the entomologists who contribute a lot in this area, he discovered that busy as a bee is misnomer. They don't do much all the time. They are trying various functions, but they stay longer in the function that correspond to their age. This is ergodicity. With they trying all of them, they stay longer, which is better for them. Similar thing, Crawford wrote a wonderful book called Arthur, Bill, and Others. Arthur was A, B, mice, and after that B, and so on. He showed the same thing that mice behave in foraging behavior. They do the same thing, and the dogs as well. So there are elements that behave like that. Now, collective behavior is like that. We have this penalty function phi. Now, in the collective, this phi depends not only upon the ith element itself, but all others as well, and its own behavior. So now collective, they're interacting all the time, and their penalty depends what each of them are doing. Special class of this interaction rule, there will be fractional interactional rule. It's like that. You have agents that perform two functions. Think about like fisherman and hunter. Each agent can be. And let's assume nu is a fraction of agents which are hunters. And 1 minus nu, these are the fishermen. And the penalty function depends upon how society, how many fishermen, how hunters they have. So that will be the function like that, depends upon nu, how many, let's say, hunters. And that obviously will be the best point for the society. Society will be reasonable when the penalty in the whole society will be the best, the smallest possible. Now, there is another rational interaction that fishermen are having this function as a penalty and hunters like this function. So now the penalty is not the same, depends only on this nu, but depends also upon what they are doing, each of them. In this case, this point will be reasonable, becomes a Nash point in the game theoretic sense. How this thing will behave when n and m are increasing. And this is the answer. When n and m, this is how smart people are, and this is how many of them are there. If it's they grow with the same speed c, in this, the nu of t goes exactly to this minimum of the penalty function in homogeneous interaction. So they are smart. However, if this limit takes place, meaning that they reproduce faster than become smarter, and therefore the ratio is equal to 0. In this case, society converges to the point 1/2. What is important about 1/2? This is maximum entropy. It becomes like statistical mechanical guess. There is no rationality anymore. So if we have a large society, but smartness is not there, society cannot operate good if everything distributed equally between the members of the society. However, if we now go to inhomogeneous fractional interaction, but there is these two curves, it turns out that there is n star smartness large enough so that for all n greater than n star, this nu will go to the Nash point, even if when m goes to infinity. So this is the story. The story tells us that communism cannot exist. Because communism, it says basically that everyone gets from the society what they want, and so equally, and there is no, and it shows that chaos. That's what results from the whole story. So that's why I did not publish. What is that? Why? Okay, we have to start. They want me to stop, probably. That's what it's all. Okay. Now, I continue this work here in the US, and again, I work closely with Pierre Kabamba and Wen Chao, you're here, Wen Chao, and Mr. Tang Chunik, they're also right here, came from many different places. Okay. Now, aiming control, I don't have time, I have to finish almost now. Aiming control, stochastic systems. There is no controller that keeps a stochastic system in any bounded domain. It always kicks it out if the noise is white noise. But sometimes you want to keep the system in the finite domain. It turns out that in this case, if we consider specification, you want to be a domain D during time interval t. In this case, you can construct controller under certain condition that it will do that. At least you will stay during this period of time. You aim something. Let's say aircraft landing on the plane and so on. So this is called aiming control, and we developed the whole theory. This is first passage time, and it came from large deviation theory developed by Franklin and Wenzel. And it turned out that the system is strongly probability controllable, meaning that we can satisfy dt with any probability p less than 1. In this case, we need that image space of vector C. This is the matrix C. It is noise, and this is the control vector. So this is image of this matrix should be larger than image space of this matrix. Physically, it means that the system should have as many actuators as the sources of noise, which is hardly ever happens. And if the things like that, we cannot have E arbitrarily close to 1, there will be certain bound. And we evaluated this bound, and it was the dissertation of Dr. Ronaldson. Congestion control of network, I'll skip conflict. This is what internet is doing today, but how you can eliminate congestion. That's work was done with Lotfi Ben Mohammed. Quasilinear control, again, this is a large area that we have developed where we transfer everything which is done in linear case for a class of nonlinear system with a linear actuator. Start again, system of linear plant, but nonlinear sensors and actuator. And the whole theory has been transferred now from the linear case to this nonlinear case using the thing which called stochastic linearization, which is like that rather than Jacobian linearization. And many things were obtained. Root locus that we discussed in class recently. So this is exactly what it is. Root locus that will not end in the saturating actuator in the open loop zeros, but there will be certain termination points and you can calculate what termination points are. Okay, now LQG, the same story. This will be Lyapunov and Riccati equation. Will be 2 more equations that give you the stochastically linearized gain in Lagrange multiplier. And work in this area was done by Pierre and Shinan Ching, Yung Soon, Javad Gokchin, and Hamid Asare. We published a book in this area. Okay. I cannot go into the time as I have just 5 minutes left here out of the 40 minutes that I allocated. All these things that we discussed that was more, it's not only theoretical, but it was not really practice directed. For the last some 30 years, we have been in the area which motivated by practice completely. And this is manufacturing systems, more the production system. Production system, the machines and buffers, and they are organized so that they produce whatever you need. This is serial line, this is assembly system. Now, problem is that machines are breaking down, people don't work as they're supposed to, and so on. You have a lot of losses in production, 50% loss production compared to nominal. It's not an unusual thing on the factory floor. Question is, how can you recover these losses? And you have now understand how things work. And we developed what is called production system engineering theory. There's many different things. This is kind of one of the main things. This is recursive aggregation that allow you to analyze how system behaves, various problems. We developed also a tool, PSC toolbox that allows people on the factory floor to figure out what's happening, who was the one who programmed this thing and implemented it. And we went to many different plants, dozens of plants we worked in, typically with a very good results. Now, so this was good, but the problem was that when we leave the plant and something happens, the same line or different, who will do it there? So did not. So we decided to develop what we call, now by the way, these are the students who work with us in production system engineering. Many of them, but they worked in other areas as well, but this is, now, Mr. Kang, you're here? People
Yes,
come, I guess, didn't come here. Okay, so we published a book. This book is translated in Chinese and used in a number of universities, you know, all over the world, I would say. But what we want now to do to develop a thing with smart production system. We want to develop a brain that we can attach to a production system. You'll get data from the factory floor. And after that, we'll evaluate what's happening and give you tell you what is the system health and how can you improve it. So we did this thing. This is the structure of this, we call it programmable manufacturing advisor. There's information, analytics, and optimization. I cannot go in detail how it is done. This is how this thing implemented. The production system, this is data measurements from the factory floor, go to this PMA. Manager tells them what they would like to obtain, what is action space, the loop is closed, and this is production improvability. This is floor work. This is couple, maybe example. An example here, it's a line that we recently worked with this thing. It was supposed to produce 30 jobs per hour, produce less than 15. So 50% throughput losses. Bottleneck is like that. Losses due to machines are like that. Losses to cycle overrun like that. Losses to buffer like that. So manager sees what's happening, why the 50% of losses takes place. And after that, the manager creates a scenario for improvement, says, I would like to improve this thing from this to this. How can you do that? And system gives them, you can do that, but you know, this thread, you don't obtain what you need. We are programmed also the same thing. So they do many different things. Who worked in this area? These are these three gentlemen. And we are finishing now this book, which are almost complete. And my time is almost done. Now, maybe I'll take a few more minutes because it's 40 minutes. So what is it that I'm talking about? What it's all about? So, Okay. In this case, I will tell you. But we need after that to various advice to, who you want to look at it. Let me give it to you while I'm taking what it's all about. You know, I wanted to work on the practical problem, but with intellectual challenge. And that's what I have been doing the rest of the span of my career. Now, I didn't join, fashionable things. I did only things that I found to be important and so on. I did not run for financial things, more grants and so on. I think that in many cases, these grants, this is kind of substitution for your curiosity and your intellectual thinking and so on. Did it work out?
Yeah, so you go.
Yeah, this is what I did. Okay, thank you, Paul. So that's what I already said. Let me continue. Now, another thing that stop it. Okay, I have probably about 10 minutes. So engineering problems typically are very complex to be solved precisely without simplification. And you have to solve them. In mathematics, you don't have to solve necessarily a problem. You don't like it, you go search for another one. In engineering, if you want to solve it, you have to solve it, So I have to, Pierre Kabamba used to say, by hook or by crook. That's what it is. Now, so how you do that? Simplification. So the motto of engineering research should be simplify. You take a practical, important problem, and after that, okay, you don't solve it precisely, but at least some estimates of how good it is. Also, I have to tell you honestly, I try to find some beauty in what I'm doing, not just put a formula and so on, but make it some kind of, see that there is a beauty in when you have like many other areas. So I guess this is what it's all about. That's what my question, what's it all about. That's what I have been doing for the last 60 years. Now, advice for the inspired. It's a promise. So PhD versus PhD. My advice is don't go for PhD. Unless you cannot live without research. PhD is a ticket to do research, either industrial or academic. But if you're not really after that, don't. It's a waste of time. I have a number of students who did outstanding PhD dissertations, went to work for industry. Now they're very big managers in big organizations. If people in their companies don't even know that they have a PhD. That's not even announced like that. So don't do that. Now, how about masters? I think masters you need to have. I've been in a bunch of meetings where people discuss promotion, and if a person has a bachelor's only, then maybe this person is very good, but it will be promoted. I knew only one guy with bachelor degree for very not famous university, Danny Pauly. He was in Chrysler with Lee Iacocca. He was right up under Lee Iacocca. You remember Lee Iacocca in Chrysler? Not really, before your time. Okay. So this Danny Pauly had a degree from some third-rate university, bachelor's, and he was the best manufacturer, vice president in the manufacturer that I have seen. He was swearing all the time and so on. He didn't become like, but he did really outstanding job. Okay, going further. Now, if you decide to pursue PhD, what you are working on and how, you have to work 10 to 12 hours a day, 6 days a week. Otherwise, it will not work out. You need a total concentration. If you have a force, you push it like that on your table, you will not penetrate. Take a needle and put it the same force, and you will penetrate it. The same as research. You concentrate, in this case, you can do that. What you want to work on, in practice or theory, they advise it both. Theory by itself is not cut these days. When I was young, theory, that was the main thing. Today, practice and theory. So you have to do something practical. You cannot say I'm control specialist. Control of what? This is where I should be able to say. Work on practical problem. Don't find the topic to work from the papers in the journals. Sometimes these papers, they say something, we do manufacturing, we do engineering, but they do something that people know about their mathematics, okay? So if you take paper from the journal, go to practitioners and investigate whether it makes sense or not. Okay, after you receive a PhD, should you look for academic or not academic? I think it depends. I will skip because time is late. I'll skip this thing. If you want to talk to me, I'll be happy to do that. Now, after you secure a position, again, which problem to work on a problem of societal importance. This is where you make your impact. A matrimonial advice. Find a spouse that will be ready to live with a researcher. It's not an easy life because kids and so on there, you want to participate in that and so, but you cannot do that. You work all the time. You sleep and you work. You wonder. This is what it's all about. But it's still, it's okay. I think the life is okay, but find the one who will allow you to do that. And finally, the thing which I give as an overreaching advice to all is like that. That is what it's about. Persistence is a foundation of success. And the last a few things which I would like to say, gratitude and acknowledgement. These are my parents. They kept me really intact. I had to behave. I had to do my work. Otherwise, I was in big trouble. And I'm very, very much grateful to them for that. These are my teachers.
It's not sharing.
Mm?
You need to go back to Zoom.
Okay. Okay. It's not sharing still. Okay, let me go to Zoom. So. Join again. This is my Zoom. This is my Zoom. And it wants me to join again. This is bad. This is very, very bad.
You are in the
Because I have to, you know what? I'll say the following. Since I don't have the pictures, I will just tell you. I had 3 PhD advisors, incredible people, Eiserman, Braverman, and Brasanoyer. The names maybe sound too good, but they were great, absolutely great. Maybe you know Eiserman, absolute stability theory classic. Brasanoyer, he was the first to prove maximum principle. And Braverman, he started pattern recognition in Russia many, many years before everything started. So I was fortunate to work with them. And also I had not my advisors, but close work with Sipkin and Krasnoselsky. That was in Russia. In US, as I told you, I met Bellman in 1966 or 67. We became friends and I learned a lot from him. So that was a very fortunate thing. Now at U of M, first I would like to acknowledge our former department chairman, George Haddad. You probably don't know him. Anyone in this room remember George Haddad? Yeah, yeah. Yeah, usually, you know, people, scientists are as good as their last paper. No last paper, you don't exist. It's the same administrators. They are not in place. They don't know who they are. George was the best department chairman I have seen anywhere in the world wherever I work. You can fight with him, you screen at him, but you're always friends and you understand what's happening. Department of EECS department before Haddad was maybe not in the first 10, but Haddad made them maybe partner at some point, we're number 4, by the way. So this is my teacher, and this is 2 other gentlemen. All of them came to U of M, by the way, gave wonderful talks here in the MES department. And this is Dick Bellman. This is how he behaved. He was very low key, like a guy like that. Now, as for UM, this is George Haddad. And this is Elmer, another, my favorite, elegant person in all, gentleman in life and research. And it seems that this picture transfers his character here. You can look at it. And this is my dear friend, Pierre Kabamba, genius, a Renaissance man. He knew everything in science, in math. He was outstanding jazz piano player. He wrote even some poems and so on. Total religion, he knew everything. We'll start working with him and some of our students, they can come, support that. We start talking about religion and culture and many different things. And this guy, look at it, they're crazy what they're talking about. But by the end, they liked it and enjoyed. You came later on. So this is Pierre, and this is a dear, dear, dear friend, unfortunately passed away very young. Now, also I would like to acknowledge my children. They're here, all of them. Would you please stand up, guys? I didn't put your picture because you are right there. And there are spouses as well. There are some spouses there that say, stand up, stand up. Okay, and there are some grandchildren also. So thank you, guys. Thank you. You know, children are difficult, but after all, it's a pleasure. Now, most of all, I would like to acknowledge my dear wife. Without her, nothing would have happened. Neither this family, and she is a pillar of this family. Nothing with me as well. So, Tejka, would you please stand up and... And finally, I would like thanks to God for giving me incredible number of acts and kindness throughout my life. And thank you all of you guys. Sure. Thank you.
You graciously ended in time for a couple questions, so ask away. Go.
I knew that you will be the first to ask. Yeah, I know.
When I first met Professor Meerkov, Semyon Meerkov,
Yeah.
in Russian, I felt that I was in the presence of a superhuman being, actually, with superior intellect, and I would never be able to communicate to him. He said, don't worry, we'll take it easy. And he just did the impossible. He raised me at least to the level where we could talk, actually, and spend some time together. So this is a person who is very modest and who has a whole teaching dimension to him that takes people who are very kind of timid intellectually and makes them flourish into whatever they come to be, faculty members, then those people in industry who are the drivers, the leading drivers. So this all different dimension that Professor Meerkov didn't mention, that what makes the people here blossom, that contributes to the papers. And as a token of appreciation, I would like to just give you your book. It's as much.
Wow. 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 Wow, Joseph. Thank you. Thank you. Thank you. Look at that. Joseph's book. Beautiful. Beautiful. Thank you. Thank you. Thank you very much. Oh, you should have told me all this story long before. I never heard it like that.
Yeah, it's 2 words, just 2 words. You invited me here to teach. I grabbed Alan Wilskis and Oppenheimer.
Yes.
I bumped into Alan. He said, "Joe, what are you doing? This is for MIT, but this is for impossible to teach. We don't teach people. We don't." I said, "Okay." I still ground this through here in signal analysis course, and then I went to Illinois. I tried that. Well, people were not very happy. I think it was still teachable a little bit. I thought, okay, this is mechanical. I'm putting PDEs. I'm making it completely impossible to teach, and this is exactly what I've been doing, using a completely unteachable book from for the last 10 years.
Wonderful,
So,
wonderful.
So we're in business, and you're in business of making impossible possible.
Wow,
With
okay,
respect to
okay.
research, with respect to solving extremely difficult problems, and with respect to bringing up students.
Thank you, thank you, thank you, thank you, Joseph. Joseph, by the way, professor of University of Illinois in Urbana-Champaign, kind of a competitor, and as far as control is concerned, maybe even above Michigan. The group is very strong. So.
Other question?
Maybe I'll ask you. Maybe you
Okay.
could comment a little bit more on your advice for research or whatnot, saying it's less theory and more practice now, but how should people still make foundational impact in that?
How many students, what?
How to make foundational impact even with the fact that there's
Yeah, yeah. You know, in my experience, contacts with reality, with practical problems, always leads to outstanding theory. They're not decoupled. So, you know, what could I don't know, advice or not, what I can say, if you're looking for a dissertation in a certain area, you would like to do research. Talk to practitioners from this area, people who work. When we started this manufacturing stuff, I would talk to people, to janitors on the factory floor, to learn from them, and certainly from managers and so on. Only after that, we analyzed, we understand what are the main topics that are important, not just from the literature, but why they are not sleeping at night. So if you will start with the reality like that, and you will find important practical problem, in this case, impact, it seems to me, just a corollary from that. So that's what I will give advice. Stay close to practical situation. Don't just write papers. No, you know, to promotion, you have to do it. But fundamentally, what you have to do is to see what is reality is, what the demands of the world. In this case, you will come up with an interesting theory as well, by the way, and impactful.
I have a question. So many of us that have known Professor Meerkov for a very long time, I'm sure feel like I do that his retirement is premature. So I'm going to ask the question I'm sure many of us are actually thinking about is, what do you plan to do next?
Yes. Thank you for asking the question, Steve. First of all, I forgot to acknowledge one thing, and after that, I tell you what I'm going to do. So for the last several years, Puya, Elavian, and Liang Zheng, we set up a company called Smart Production Systems. And it's very, very, you know, just three of us, and we're doing various things there. So first I want to acknowledge you and Liang. You guys helped me to set up these view graphs as well. So thank you very much. It reminds me even more so. This thing did not work when I talked about it. I forgot, and I apologize for that, to acknowledge. So Steve, thank you again. I thank you for many different things. Thank you. Acknowledge 32 doctoral students who worked with me during the last 60 years. I hope, guys and girls, that you learn from me as much as I learned from all of you. So that was always incredible pleasure to work with all the students that I had worked. So, and I forgot to do that. And of course, wanted to mention you two guys who helped with many different things. So what I plan to do, we have a lot of things, Steve, that we plan to write. We have a bunch of papers that we have to write about the manufacturing mostly. And that's what will going to be the activity that I plan to continue for sometimes, as long as Almighty will allow me to do that.
I got one more question. One more question. Yeah, good morning. All these production systems are about production factories. Like, what is the ultimate factory?
What- Optimal factor?
Yeah.
I don't even know what it is. If you talk about the specific plant, I can tell you what a specific plant, what will be optimal, not optimal, whatever it is. That's a plant is set up to produce, let's say, 60 jobs per hour, assemble 60 cars per hour. It is typical in mass production automotive. 1 minute you have to produce a car, okay? And in many cases, they're producing 30 or 40 jobs per hour. So there are this 20 or 30 jobs lost every hour. So the question is, find where the losses are, eliminate those losses. And this is what you have to do in production, in manufacturing in general. This is what the goal is. And this is what we have been doing to the last, 35 years. In fact, I came to Michigan for this specific reason, to be close to manufacturing. It's exciting area. It's not really glamorous area. There was a guy who was vice president of General Motors, Gary Kauger. He's now in the board of our small company. He retired some years ago. Outstanding manufacturing engineer, member of National Academy of Engineering, by the way. So he used to say, manufacturing guy never gets a girl. It's not like cosmetics or banking, just a manufacturing guy. You smell best. So, but this is the most important thing, because the wealth of a nation comes only from two sources. One is from the ground. You can either grow it or you mine it, like Saudi Arabia, for example. And the other one is manufacturing. There is no any other sources. Like China, for example. China today is a rich country. We borrow money from China. What made it so rich? It's manufacturing. So now, people could become rich without this manufacturing and resources. You just rob the bank or you cheat on someone, and so you become rich. But nation cannot be rich unless these two sources. So although we don't get a girl, but we can do something useful for the country. Thank you.
Well, thanks, everybody. Let's give Semyon what do you think? What do you got?